let's take a look online. And I did post, if you will, the test answers. So you have all the test answers from test 1 to test 4. Now, I went through the answers very quickly. I may need to double check on a few things, but at least it gives you what to look at. You have written down, you should have had written down your work and your problems, so you can kind of compare the answers that you're getting there to what would be expected. So at least you have something to look at. And you also have for test 1 through 3, the same sort of thing as well. So our test tomorrow is essentially test 3 and test 4. So you can take a look at those test 3s and see some of the things that we had on that test. So these are the types of problems that you'll be asked to look at. And then we'll have a review on Monday for the part 1 or the second version, or second, not part, but the other aspects of the final exam, which will be on test 1 and 2. Now, they're not exactly 50% each. I think the one tomorrow is just a little bit less, like 46 and 54. Now, the chapters that you need to focus on for tomorrow, and I'll let you know we're not going to be putting in, if you will, anything on the conics. So we'll kind of let that go. So that's one thing you don't have to look at for the final exam. But, tomorrow we have what we're calling part 2 of the final. And this is on chapters 8, 9, 10, and 11. You are going to skip 12. Those 12 on conic sections, you don't have to focus on that. It's a topic that I want you to see, but it's not a topic that I'm going to emphasize. So that's what you want to look at. And these are essentially test 3 and 4. Kind of did this first because you just got out of test 4, so half of this stuff is kind of, right there in the front of your brain. And the other half, then you can kind of get back up to speed over the weekend. And then on next Tuesday, Monday we'll come in and we'll kind of do a review. Then we have our part 1 of the final part 1. And for this, it's chapters 1 through 7. And like I said, this is like, 46%, and this is like 54%. There's actually a little bit more in there, so that's why this is like 4 and that's 7 chapters. But some of this stuff in here is very meaty, and there's a lot of stuff in there. And again, this is test 1 and 2. And you do have access, and as soon as you grade test 4, you'll have access to the test questions as well. But you do have access for your written responses for test 4, but you have access to opening up test 1, 2, and 3. Hopefully everyone knows, I went over that early on, how you can get access to the questions. You have to click on the grade after you click on the test. Like so, some people may not have that. Let me just double check. See if I can do that or not. Let me try over here. See if I have something in here. Okay, I do. Okay, so let's say you wanted to find out what was on the test. You go to my grade section, click on a test over here, and it gives you a grade. If you click on the calculated grade, it'll kind of give you all of the questions there, and you have your written responses that you can use. Now, in this test and some of the other ones, I put the link here. What I'm doing on the final exam, the last problem on the final exam, is going to contain this Desmos link as well as a link to the formula sheet that's at the back of the textbook. So they have all those trig identities and logs and exponential information will be there. So you have that at your disposal. So that's at least something that you can be aware of for tomorrow. I have you, able to work on it for like 100 minutes should be enough. I think there's like 11 parts to it, to the both of them. The information that I just put there is on problem 12 on both of them. So at least you'll have that as a resource. But this is everything you need to know about getting ready to take a calculus course after this. So if you have a good handle on most of this stuff, you should do okay in the calculus. Here, this is a little more, this is the analysis, both the analytical trig and exponentiation and analytical geometry. This is the basics of functions as well as analytic algebra, all the algebraic techniques that you need to analyze things. Completing the square, long division, partial fraction, decomposition, all these algebraic manipulation routines that you have to go through to make things work. Whereas here, this is analyzing the functions and their various, geometric properties, if you will. As well as some of the trig identities and learning how to manipulate trig expressions and showing that they are two trig expressions are equivalent or not equivalent. So you have access now to all of the test answers, so you can kind of use those to kind of figure out. Again, over here, what's not included. So we are going to exclude the conics. So that is not a requirement there. So, I mean, it's good to know, but not something that if you didn't know it, you could still be very successful in the calculus. The other things that you really need at different times, either Cal 1, 2, or 3 going forward, so at least I've seen it. We'll review it again when you need it in the upper level calculus courses, but it's good to have seen it prior, so it's not the first time you're seeing it. You're kind of refreshing your memory about what it is, and you're better able to handle it. We do cover topics here that are used throughout calculus 1, 2, 3, and even 4 with our differential equations. Any questions? Any general questions?
I have a question for tomorrow for the final. Are we allowed to have a sheet with the formulas for like the compound interest and the decay and growth?
Yeah, if you want to have one sheet for that, that's fine. Just hold it up at the beginning, so that's fine. It makes me feel a little, because that's I'm not having people memorize a lot of things. If you use something enough, you will remember it. And that's what there's so many different things here. So, but if you know how to, work with them and analyze them, that's the important thing. And I'm giving you all the trig identity formulas. You see it in the textbook that you had on the other test. So they are the, and it's the last problem. So if you really want, you can go to the last problem, open that up, open up the Desmos browser in Respondus, because I have that enabled. You have that available to work any of the problems using that. Any other questions? So make sure you kind of watch the time and make sure your computers are good, everything's stable. A few, not necessarily in this class, but in other classes, some people had glitches in there, whether or not their computers were working properly, and that can cause an issue. But hopefully everything goes more smoothly, and you know the process now. The Respondus is really just a visual image of the test. The real test is what you write down, because that's what I focus on, and make it as close to reality. That's why another reason I don't like. Some students and professors like multiple choice because it gets automatically graded. And students sometimes like it because then they at least get a thing to guess from. But for most part, when you're in the calculus, it's life in general is not multiple choice. You have to figure things out and understand, what sort of problem is this, what tool applies, and how do I apply it? And that's really what we're focusing on. That's why I am not a big fan of multiple choice questions. I like regular, write it out, work it out, because that's how you really learn something, not by guessing. And that's a major failure of our, secondary school system with the regents. They are multiple choice tests for the most part. There are some others, handwritten parts. And what does that mean? Well, just by purely guessing, you could take someone that never took the course before, take a 4-year-old, and if they can just pick A, B, or C, or D, go through the test, they could get almost 20% on that test. And it turns out that for the Regents exams, it's for some of the earlier the basic algebras, they call a passing grade of 65, that they gave a 65, was actually a raw score of about 32. So you got about 32% of the knowledge, but 20% of that 32%, of that, well, 2/3 of that, you could have got just by guessing. So what they do is they take students and they say, oh, well, you passed the Regents, but they may only know about 20% of the material. And then they say, you're in the next Regents class. And it does not work to go to the next course with knowledge of only 20%. It's a bogus thing New York says, so they just want to pass so many people, so they just put them through. Now, if you get a higher grade on the Regents, that's more closely aligned to the actual, the raw score and the score you get on your, card for, your passing grade for the course, and is more closely aligned. Like a 90 is probably closer to, it might be an 88 or something like that, as opposed to a 65 being equivalent to a 32. Big difference there. That's why, most people don't like to, because it takes me so much longer to grade these things too, because I have to write them out. But I can't wait till I'm back face to face. That way I can write on the tests and you can take them back, because it's very hard to write on these tests. It doesn't work out that way. But any other questions? Hopefully everyone's, learned something. I know there's a lot of work. We cover a lot. We met 4 days a week for almost 15 weeks here. There's a lot of different homework and work that you guys did. But that's how you learn something. It's a language. And to speak the language well, you have to speak it often and in many different settings and stuff. So hopefully you put the time in, and it'll be time well spent, because when you hit the calculus, you can focus on the calculus concepts and you'll have a lot more of the algebra behind you. Because there was a lot of algebra all throughout. And I still notice students with some difficulties, but hopefully it's getting a little bit better. And when you get to the calculus, you say, okay, I remember this in pre-calculus. It's not so bad. Let me focus on the calculus concept, and I don't have to worry about the algebra. That's the whole purpose of this.
I just have a general question.
Hmm?
Do you know, like, the, what's it called? Like the letter scale to the grades?
Yeah, this is the letter scales that we have here for something. This way, there is no A plus, but you have an A, which is essentially 90 to 100. And when I give you your grades right now, don't look on Blackboard for your your final grade. That's not going to be your final grade. It computes a final grade. I couldn't shut it off. I'm going to put in a separate column that'll have your numerical grade, and it'll also have a letter grade. So over here, then you have like a B plus, and that's usually in the range of 85 to 89. A B is 80 to 84. C plus is essentially 75 through 79. A C is 70 to 74. There are no minus grades. We don't have them here at the college, but we do have the plus grades. And that is my 65 to 69. A D is 60 to 64. And then anything below that, or 60. So that's how, and I'm going to give you both on your final grade when you look at Blackboard. There's a column that will show you your number score as well as your letter score. And then I will also be factoring in there the homework too. At least you'll have that to go by. And this is also, if you look, it's also available in the college catalog. You just look under the grading scale, they'll have it there as well. Any other questions? General or specific? Sure. You can do the same thing for, Monday, be looking at some of the other ones. So let's start with this chapter 8. Uh, 15 and 16. So number 5, we're looking at solving a triangle problem over here. So what we have, essentially, I'm going to put what we have. This is angle A, angle B, and angle C. There's my angles. And A, B, and C. So typically we always have 3 out of the 5. So here we have 64 degrees. And A is 6 and B is 5. Okay. So what we have is we don't have enough to start with the law of sines over here. Law of sines, we usually need 2 of one and 1 of something else. So what we could do is we could actually solve for, if we wanted to, doesn't matter, but I'm going to solve for length C over here using the law of cosine. So we have that, and you'll have this, I believe it's on this, I believe it's on the trig thing. You can double check that. C squared is equal to A squared plus B squared minus 2 AB cosine of angle C. I think that's what we have so far. So we can actually plug everything in, and then we'll just kind of find our value of C. Let's take a look at C. I just want to make sure I put that on there. I think I did. Yes, we have the law of sines and cosines on that sheet. Good. So I just plug everything in. I'm solving for the C, so C squared is equal to 36 plus 25 minus 60 times the cosine of 64 degrees. So we'll plug everything in and we'll see what we get on our calculator here. Go to the degree mode. Always check to see what mode you're in. So 36 plus 25 minus 60 times cosine of 64. So C squared in this case is equal to 34.6977. Take the square root of that. And I get C is approximately equal to 5.89, but since I only know these to the whole numbers, I'll get the approximations to 1 additional decimal place. Okay, now what can I do? Well, now I can use this angle, this combination to either find angle B or angle A using law of sines. Doesn't matter which I go to. Let me go and use this together with B just because they're closer together. So now I have that the sine of B, over length B is the sine of C, angle C, over length C. I'll plug that in. So I have my sine of B. That's what I'm looking for. All over, well, B is 5, is equal to the sine of C, which is 64 degrees, over the approximation 5.9. Now, if you wanted to, you might get slightly, if you want to use 5.89, that's okay too. So I just multiply by 5 and I bring this over, and I have my sine of angle B is equal to 5 times the sine of 64 degrees all over 5.9. And what do? I have to take the inverse and cancel out that sign to give me the inverse function. It's not the reciprocal, it's not the cosecant, it's the inverse function. But I do that to both sides. This cancels out to just give me B, angle B. Now we plug it in over here, and we may do some double checking as well. I'll plug that into my calculator. It's going to give me my angle in degrees out as well. I take the arc sine of 5 times the sine of 64. And divide that by 5.9. And close that off. And in this case, I get approximately 49.6 degrees. Okay. Now, is there any other possibility? Remember, the sine could either go from, it goes from minus 90 to plus 90. Could I get another, essentially moving from 49 and moving it over another 90 degrees? You're not going to be able to because of that 64 degrees. So here's the approximation for this, 49.6 degrees. And then I just use that the sum of the angles have to add up to 180 degrees. So I get angle A over here is equal to 180 minus 64 minus 49.6 degrees. And I get 66.4 degrees. And that's another approximation.
Excuse me, Professor, I have a question. How would you find out if there was another triangle?
Yeah, it's what you get, this, because when you do the arc sine, physically what's happening is this. Now back to our, whole unit circle, if you will. A lot of roads lead to the unit circle. The arc sine will only give me angles in this realm over here. Goes from minus pi over 2 or 90 degrees to plus pi over 2. That is its range. That's the output of it. So in this case, it gave me this angle right about here for this particular one over here. Now, is there another one where I could get the same sort of thing? Well, if it does, it would kind of go straight across over here. And it's not going to give me that. It's just going to, because it might give you something down here, or it could give you something way over here. And in this case, if I had something like that, it would kind of map this over to here, map it over to the negatives. So this one over here, if it was, say, beyond 90 degrees, when it goes through here, it's going to map it over here. So that's not the one I'm looking for. It would be something that's way over here. So that would be the 49 plus another, essentially 180 degrees, and it would not, kind of work out in that regard. You couldn't, take the 49, subtract that from 180 degrees to get the amount, and you'd have that sort of thing over here. It has to be within that realm. So, because if I picked another value for this, by adding that additional, say, 90 degrees to that, you can see that that is not going to give you, because of the 64 that's still there, it's not going to give you that other viable option. So it kind of closes that out for you right there, if you will.
So is it that you would add the 49.6 to the 64?
Well, yeah, but that's going to give you right there. That's going to give you 100 and something. And you see if there's another angle that would give you the same output as the 49.6 degree angle, would that work or not? Let me just kind of show you specifically. So for example, we take the 180. So I want to test this out. We take this angle, so take 180, and we subtract off 49.6 degrees. Okay, that's another possible angle that will also give you the same. So when I plug that in, it might be it might just one that works out here. Let's just double check. 180 minus 49.6. This gives me 130 degrees, or 30.4 degrees. So if that was the other angle, and I tried to add it to the 64, it wouldn't work. I need this to be smaller than when I add it to angle C. I still have another angle that would get me 180 degrees. And the other thing here, you can kind of see that A is the largest. A is the largest length side. So that has to be the largest angle. That's another reason it's going to stop. So what you do is you get your value out when you use your arc sine. Subtract it from 180. So it gives me two possibilities. Because I can take the sine of 49.6 or the sine of 130.4 degrees, and it'll give me the same value. But if I add 4 to that, well, that's going to give me 194.4 degrees. That's above 180. So two sides are adding up to more than the 3, so I can't do it. But now, if this had turned out to be something like, they say, in this case, it's not going to be so nice because of A is the largest side. That's kind of a bit of a problem, but that's okay. So say if it turned out to be a larger one, say this was 67 degrees or something like that. Well, it can't be that because it's the longest side. So say it was 61 degrees. No, it's these sides too that are mattering. But let's just forget those things and say it turned out to be that I was subtracting, 80 degrees from that. Okay, so 180 minus 80 would be 100 degrees. And then I could add 64. Well, I still have some room for another possible angle. You could have another one that's 26 degrees. It's not going to work out because that's the smallest side. But you just take whatever angle you get out of your arc sine, subtract it from 180. That gives you another angle. And if it contradicts, meaning the sum of the angles have to be 180 degrees, you don't have to check for it. So that's all it is. So that's just kind of using law of cosines, law of sines, and you now have solved your triangle. And then you said 15 and 16, I believe. Well, solving triangles. Usually students do pretty good on solving triangles, for the most part. Let's see, 15. So solve the trig equations below under given conditions. Is equal to a negative 1 over the square root of 2. And we're on the interval from 0. So 0 is less than or equal to theta, which is less than 2 pi. Now, you might recall that this is equivalent to, remember, this is equivalent to minus the square root of 2 over 2. They're the same thing. Now, for this one, that's one of those special numbers, so I would go right to the unit circle. So I'm looking at here my unit circle over here, and theta is as I go around that unit circle. And I'm looking for when my sine value, that's my y coordinate over here, is minus the square root of 2 over 2. So it actually occurs at two different locations. It occurs here, and it occurs here. Those are the two angles. Because this over here, my x coordinate is 1/2, or minus 1/2 on this side, and minus the square root of 2 over 2, or minus 1 over the square root of 2. This is positive 1/2, and this is plus, minus the square root of 2 over 2. The y coordinate is negative. So what are these angles? Well, each of these is 45 degrees as I step along. This is counting pi's over 4. So 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, which is pi, and that first angle there is 5 pi over 4. Now, if I count to this one, that's 2 more pi over 4s. So there's my 5, 6, and then 7 pi over 4. So that's my answer to this. It's either 5 pi over 4 or 7 pi over 4 is the solution to this. This is the exact one. So theta is exactly equal to 5 pi over 4 or 7 pi over 4. Now, if we want to, validate this, you just, sometimes it's good to just, put this on your calculators and see if you can get it to work out. I'll set up a calculator over here. I think I have one ready. Here we go. So turn this on. Again, let's clear this out. Let's see what mode I'm in. Okay, degree mode, which is not what I want to be in. So I'll change it over to my radian measure. Or I could put the actual degree angle, but usually you stick with radians. So you're just taking your 7, a sine of let's start with 5 pi over 4. And you're going to get a decimal. And then if we plug that in, change the sign of 1 divided by the square root of 2, you get the same exact answer. Or if I want to turn around and do the sine of 7 pi divided by 4, I get the same exact decimal. So that essentially solves that problem. I have my two solutions, and I did it all without even needing a calculator, because that's one of those special values. And then you also mentioned 16. Some of them we can do exactly. If we can do something exactly, we always prefer the exact approach. Because we know if we come starting with exact, and we have to do approximations. If we're in some sort of science or engineering discipline, we have to do approximations. Then we know the impact of our approximations, because we know what we're dealing with. We don't know what happened before that. So 16 is the following. We have the tangent of theta is equal to the square root of 3. Now remember that the tangent is the sine over the cosine. So again, we're also given no restraints. So this gives us some condition over which to look. This, however, has no restraints over here. Well, let's start with the unit circle, because we know that's a square root of 3. So does that give us anything to kind of contend with? So remember that the tangent is the sine of theta over the cosine of theta. So that's essentially your y coordinate over your x coordinate on your unit circle. So if I'm going on my unit circle again, and I recognize, well, say y was equal to the square root of 3 over 2, and x is associated with 1/2, what do I get? I take the division of those, that gives me the square root of 3. So I'm looking for when my y value is square root of 3 over 2, and my x is 1/2. So let's kind of look at this unit circle, and I'll start to draw some of them in. So over here, this is when my y is square root of 3 over 2. And this could also be positive and negatives as well. You'll see what happens when I get double negatives. It will also work out too. square root of 3 over 2, comma 1/2. Let's see, x is a half, y is square root of 3 over 2. This is the problem over here, because now this is minus, so that would be minus the square root of 3, so that's not going to work. This one over here would work because they both happen to be negative. So if I come over here and I have the same angle over here, this is minus the square root of 3 over 2, comma, negative 1/2. The same thing, so negative and negative. Divide two negatives, turns out to be positive. These other ones would give me minus the square root of 3. Let's start with one rotation around, and then we can kind of keep going around and around if we want. So what is this angle over here? Well, this angle here is just pi over 3. It's 60 degrees. And then we can count pi's over 3's over here. You can see there's another one. This is 2 pi over 3, 3 pi over 3, and that's 4 pi over 3. Just counting pi over 3. So if you want 60, 120, 180, 240. So that's the other one. And those are my two angles here that start out with. So let's start and write it this way. So my theta then is equal to pi over 3. Okay. Now, if I wanted to get another one of those, I could just go around in a positive way. You get a lot when you have no restrictions here. Then you can have a lot of, you get infinitely many. You got to try and look for the pattern. So I could add, essentially to this 2 pi to that and kind of get it to work out. So, and this 2 pi is 6 pi over 3. So it's plus 1 is 7 pi over 3. And then I add another, essentially 6 pi to that, comma 13 pi over 3, dot, dot, dot. So it gives me going this way. But I could also go in the negative direction if I wanted to. So I could get this angle here, start here, and go all the way over here. And this would be minus 1, 2, 3, 4, minus 5 pi over 3, if I'm not mistaken there. All right, so I go 1, 2, 3, 4. So I could have equal to minus 5 pi over 3. And I could keep going around another 2 pi, which is subtracting another 6 pi over 3. So minus 11 pi over 3. Another 6 from that is minus 17 pi over 3. These are coming from just that one value there, dot, dot, dot. Now let's work on this one over here, which is 4 pi over 3. So theta could be 4 pi over 3. Or I could add another 2 pi of that, which is 6 pi over 3. So it could be, in this case, 10 pi over 3. Another 6 pi added to 6 pi over 3 added to that is 16 pi over 3, dot, dot, dot. Or I could go flip it around the other direction. I could come around here, and this is equal to negative 1. Negative 2 pi over 3 would give me that. So I get my 1 over here. Let's really 1 down here. 2 pi over 3 and another pi over 3. So theta could be minus 2 pi over 3. And then I'm going to subtract 6 pi over 3 from that. So minus 8 pi over 3 minus another 6 minus 14 pi over 3, etc. Complicated. Lots of different things going on there. So without that restriction, that opens up a whole can of worms. Now, if you didn't get all those, would you lose a lot of points? No. But that's typically what is involved when you kind of take the training wheels off. It kind of keeps you in a reasonable range. This is with the training wheels off. And you could verify that. And let's just see what the square root of 3, let's take a look at its decimal and just kind of verify everything using our calculator. This is just to validate everything there. I'll come over, let's clear this out. Let's do the square root of 3. So what decimal are we looking to approximate? There it is. So let's start with the tangent. Let's just take pi over 3. Second function, pi divided by 3. And we get that. Let's take one of the crazy ones, minus 8 pi over 3. So tangent minus 8 pi divided by 3. I get the same exact. I pick any of those values for theta, I'm going to get the same thing. Let's try another one. 16 pi over 3. And if I look at that, I always get the same answer. So I have infinitely many solutions. Kind of hard to see the pattern. The pattern here is I keep subtracting 6 pi over 3. Here I keep adding 6 pi over 3 once I start out. Keep subtracting 6 pi over 3. Keep adding 6 pi over 3. And there it goes. Be hard to set up a pattern over here because 1, 7, could go 1, 4, 7, 10. Yeah, so I could set up a pattern. I could combine these two together and those two together and set up a pattern, but I'm not going to call it. That's number 16. So that is chapter 8 practice test. And then I think you also said something in chapter 9 practice test there. But did this help a little bit, seeing this? If the more you see it, the more it helps. And that's why if you see things over and over, you start to see things. The first time you look, I show you something, you only get about 10 to 20%. And then once that is kind of solidified in your brain, the next time you see it, you get another 10 to 20%. And then you start filling everything in until you, okay, now I really see the full picture. So number 27, and you have, say, a bacteria double in 48 minutes. So some bacteria, I'm not going to worry about the name of it, doubles in number in 48 minutes. If you become infected with 1 dozen, so your initial infection amount, A0 is a dozen or 12. How many will you have in 1.5 hours? So after, T is 1.5 hours, but we have to be careful over here. This is minutes, those are hours. So let's just turn everything into minutes. I could turn the minutes into hours, but I'm going to turn the hours into minutes. So that's, 60 plus another, half of that. So that's 90 minutes. 1.5 hours. We'll keep everything kind of the same amount. Okay, so we have the doubling time, and then we just plug it into our formula. So my A, the amount over any time period, is some A0 e to the, and we have our doubling time. So we kind of see our doubling time is 48 minutes. So e to the, and it double, so we have my natural log of t, so let me see if I get that, minus natural log of 2 over half-life, minus natural log of 2 over the half-life times t. Okay, so half-life we have is 48 minutes, so then my A of t is A0, which is 12, e to the minus natural log of 2 over 48 times t is 60. The minutes will cancel out. So let's plug that into our calculator. Let me use the one here so you can see exactly what I'm plugging in. I'll clear this out. So I'm going to take my 12 e to the minus natural log of 2. 2 is for doubling. Times 90 divided by 48. Putting the 48 behind. If I did divided by 48 and multiplied to 9 times the 90, it would be okay, provided into any sort of decimal, adding parentheses in there. Oh, this is increasing. Excuse me. It's plus. I don't know why I went plus, not decay. So I got to go to plus. My problem. 12. I did if it was decreasing instead of increasing. Everything's the same except we go and increasing exponential as opposed to a decreasing. Yep. That just kind of make sure we have that correct. So the same thing over here. 12, second function, e. Oops, excuse me. Second function, e. There we go. And then I take natural log of 2 times 90 divided by 48. No, what I have, yeah, I'm using the wrong thing on top of my head. So let me not finish this. Let me go back to this a little bit quickly so we can kind of see. I usually don't like when I double. I usually like to go 2. So what we're actually looking at is this. So we have RT. Okay, that's what we have to do. We have to find the rate of increase. So this is the model, e to the RT. That's our rate of increase. We're given the doubling time. It doubles in 48 minutes. So what we do is we have to solve for R over here. That's a little bit more detailed. And what do? I hit a point. I'm going to hit a time when my A0 is, A is 2 times A0. So when T is 48 minutes, my A0 is equal to, my A is 2A0. So I get 2 times A0 is equal to A0 e to the R times 48. So that's what I'm looking for. I have to find R. I'm looking for an increasing exponential. Starting over here at 12, and I want to see how it goes up. This, I can get rid of the A0s. I can take the natural log of both sides. So I get the natural log of 2 is equal to the natural log of e raised to the R times 48. Just gives me 48 times R. So in this case, R is the natural log of 2 over 48. It's going to give me the same result that I had over there, but it's the same sort of thing. So my R now is the natural log of 2 over 48. Same thing I was going to have a moment ago. So this is my model. A is equal to 12, or A of t, if you will, is 12 e to the natural log of 2 over 48 times t. Now I want to find out how much is there when t is 90 minutes. It's just a short increase. See, I should, it's more than doubling. So I wanted more than double. Let's see what it turns out to be. So in natural log of 2 times 90 over 48. Essentially what I was typing there and writing there, but just to be a little more precise, because it's an increasing as opposed to a decreasing exponential. So coming over here, 90 divided by 48. It's the same thing, but it's just a different way of looking at it. And I end up with 44. We round downwards. Even if it was like 44.7, I'd still round downwards over here. So in that time, we went from 12 to now 48. After 1.5 hours, I now have 48. So, went up 4 times, if you will. 4 times that. It went up by a factor of 4. And I think you said, was it 29, was it? Okay, this is our Richter scale with the logarithms. This is good. Kind of shows you how they're kind of used for some basic problems. You're going to, the course of your studies, you'll see some more complicated, much more complicated uses of them. These are the elementary ones. So an earthquake measures equal to 2.4 on the Richter scale. how much larger is it from the next largest? So remember, m is equal to the log, common log, log, or I just put it at that, of a over a0. There's my a0 is kind of like a space standard. That's the normal vibration. You want to see what's happening above that level. So it has a little bit of, if anytime you listen, it's got a little background noise, so to speak, and you want to see what percentage above that. So this is what I'm solving. Remember, this is related to a log in the base 10. So I need to take the inverse of this. So what do? I have this 2.4 is equal to the log, it's essentially the base 10 of a over a0. To get rid of that, I raise both sides 10 to that power. So I take and I want to get the relative relation between a and a0. That's what I'm looking for. So if I take this side and raise it to that power and that side raise it to that power, what happens is I get on the left-hand side 10 to the 2.4. This cancels out. It gives me a over a0. Well, I can plug this into my calculator and get an estimate for that. I'll just do it here. We'll go to it, but I'll just take my 10 and raise that to the 2.4 power. And I get roughly 251. This is about 251. Now I can solve this for a. So I get a is 251 times the normal background vibration. So it's 251 times larger. So instead of this, it's 251 times bigger than that. It's a logarithmic scale, and it scales it down. Now, the Richter scale has been modified over the years. This is the first one he came up with, but it's been added to and refined because we know vibrations tend to go deeper in the surface, and they look at surface vibrations versus deeper vibrations. There's all these different modifications on it to make it more sophisticated over the years. That's all it is. It's just a rescaling, because most people don't like large numbers. So if you take, a Richter scale from, say, 3 to a Richter scale of 9, that means the one that's 9 is, essentially 1,000,000 times larger than the other one at a Richter scale of 3. M of 6 corresponds to 1,000,000, shifting of 1,000,000 times. It really scales it down because the logarithm scales down large numbers. Just remember what the log function looks like. At large numbers, it flattens out. So for large numbers here, small numbers. This is the scale of the Richter scale on this side, and this is the argument of that log function. This is my a over a0 scale. So it takes a large number here to make a small movement there. And that's what it's used for, to deal with things that traverse over a large range of items. So that's number 29. Anything else? Well, in this case, I think it just says, let me just read through again. Where is it? It just says, how much larger is this than the smallest detectable amplitude? So the answer is 251 times larger. It's always done relatively. You're not given, it's always relative to them. How much larger? Well, it's 251 times as big. So you don't need to, well, you're never going to be given the A0 in this course. Now, if you were there, you might look at certain parts of the world. They may have a larger baseline, which they have to kind of adjust for and account for. There may be some normal manufacturing, heavy machinery in areas that will cause a larger background vibration. And that's what they have to factor out when they look at things and they see some natural causing things. When they suddenly see something, did North Korea, the Russians, did they set off a nuclear weapon? That's how they do. They check and monitor, and you see, reverberates across the entire globe, and they can say, there's something out of the ordinary, and then they can estimate the size, how big, and how many megatons was it that went off. That's why there's very sophisticated analysis that goes on for our protections as we go forward. But that's it. It shows you there's very simple applications of these functions and their usage. And so math is kind of so critical in that regard. So that's 8 and 9, and then 10 and 11 we just did on the last test. 12 is excluded, so hopefully it gives you a sense for that. Now there's also in chapter 8 some of the trig identities and stuff like that. We solve some trig equations there. And then we also do some more trig on test 1 and 2, really test 2 when we were dealing with the angles and degrees or radians and those sort of things, and some simple calculations of those. So those